So you recently published a book titled Code That Fits in Your Head. I assume that code that we wrote is sometimes too big, too complex. Is that something that you're trying to suggest by writing this book? Or is there any kind of problem that you see that you try to tackle by writing this book?
Well, so the book actually started out more as a catalog of software development, software engineering heuristics, because I spend a lot of time coaching various different software development teams over the last decade or more. I discovered that there were certain explanations and certain rules of thumb that people kept asking me the same questions, basically, and I kept giving them the same answer. So I thought, well, okay, there's actually a catalog of things here, ideas. Some of them I've learned from other sources, and some of them I sort of figured out by myself. So I thought it's probably worthwhile to connect all of those things, but we also need a little bit of a backbone, a thesis to put a lot of those things together. And particularly with the things that I've tried to figure out by myself, I've been thinking now for quite a few years that one of the things that makes software development difficult is that one thing is writing the code, but as Martin Fowler says, any fool can write code that a computer can understand. Good programmers write code that people can understand. That's from his book, Refactoring. And that interested me quite a bit because I think what makes software development hard is sometimes writing the code is difficult, but it's more the fact that you have to go back and read what was already written and try to understand what was the purpose of it and why was it written in that way, what's it actually doing, and where can I insert some new behavior into the existing code. So we spend much more time reading code than we actually spend writing code. And I have this thesis that runs through the book that one of the reasons why we're having trouble reading code is that the human brain has certain cognitive constraints. There's just so much working memory that the brain actually has, and it's quite limited. On the other hand, a computer has a completely different way that its memory works. So if you only take into account the computer's memory, a computer can juggle 10,000 global variables if you wanted to. That's a famous case with Toyota. If you look up something called the unattended acceleration bug, they figured out that maybe they actually had about 10,000 global variables in the code that ran the car. Well, okay, so I'm digressing here. But basically, a computer can easily juggle 10,000 things at the same time, and the human brain can juggle maybe 6 or 7 things. So the guiding principle then becomes to see if you can write code that takes into account not the memory limit of the computer, but the memory limit of the reader. So that's basically the idea, and that's why the book is called Code That Fits in Your Head.
I'm sure that almost all developers here, the listeners, me, myself included, we have seen code that probably cannot fit in our head. First is like it's too big. It's either too many lines of code in one class, for example, one function, or just too many variables or too many things in one go. And then also at the same time, sometimes you have to jump into multiple files in order to get the full picture of certain things. I think we all have been there, and I can see this is a real problem. And when you mention about human memory limit, I think that speaks why that sometimes we struggle to read the code. You mentioned that software development is hard. Most people, predominantly from the business side or product side, they will think that writing software is easy. For software engineers, sometimes we think it's not that easy. Why do you think there's this mismatch? Like when you say software is hard, can you explain a little bit more? Why is it really difficult?
I think complexity grows exponentially with software. So writing something like Hello World is not difficult. Most people can do that. Getting started with things that are a little bit more complicated than that is, again, something that most people can learn. That's one thing that might influence the way that people from the outside look at the industry. They say, well, it's easy to get started, so why is it so hard? And you see this very often in projects, development, software that starts from scratch, from greenfield. The first couple of months, things actually go pretty well and developers move at a good pace. And then as time goes by, things start to be slower and slower. One problem with the other stakeholders is that often they discover that velocity decreases. They discover that too late. And then they start to complain about, why is everything going so slow? Oh, the developers must be lazy or something like that. You often get that sort of response. So I think there's a problem from the outside is that, first of all, you have this sort of exponential growth of complexity as time goes by. If you don't do anything to manage that complexity, that's one thing. And I think another thing is that there's a disconnect between how easy it is to formulate a problem and then how difficult it actually is to implement code. So there are things that are difficult to write. There's still a frontier where people are trying to figure out how do we do all sorts of advanced artificial intelligence, whatever people call it these days. There's still things that are hard to do. There's this famous XKCD comic where they say something like, someone comes by and starts giving the software developer a set of requirements. The person said, that's the stakeholder. The stakeholder says, we need our application to be able to identify if a photo was taken in a national park. And then the developer says, oh, that's easy. We just look at the coordinates of the metadata on the phone or the photo and correlate that with a national park. That's easy. And then tag it if the picture contains a bird. And then the programmer says, okay, I'm going to need a research grant and 10 developers in 10 years, because that is as easy to say, but it's an order of magnitude more difficult to actually implement a feature like that. So we have this disconnect as well, where people who don't have the technical insight, they often get completely surprised by how difficult or hard things are. We even get surprised by that ourselves. Sometimes we get a requirement and we say, oh, yeah, I could do that. I could do that in a week. And then when you start diving into it, you figure out, oh, this is actually really difficult. I have no idea. I thought it was going to be easy. I don't know. It's going to be really hard. So that happens a lot in software development as well. So I'm paraphrasing, and I apologize that I can't remember what the source was. But someone said something like, in software development, copying things is free. We do new things every time because we never do the same thing. In industry, you may build 1,000 copies of the same car because there's actually a cost associated with creating a copy. But there's no cost associated with creating a copy in software. So we never actually spent much time creating copies. Everything we do is always producing new things. When we're producing new things, it also means we do things we've never done before. So we're constantly engaged with doing things that we have never done before. Sometimes it looks like something we've done before. We have some experience, but we're always doing new things, because if we weren't, we could just have copied what we already have created earlier on. Some development organizations call their development part, they call it R&D, research and development. And I think that's actually not too far from the truth. We should probably recognize more that most software development organizations are actually research departments. That might actually go a bit of a way towards setting expectations a little bit better. That last part is something that just occurred to me right now. So I haven't really thought that through, whether that's a good idea or not. But that's at least worth thinking about it, I think.
In your book, the first few chapters, you are talking about the metaphors of software engineering versus the physical or mechanical engineering, which has been
Right.
around for quite some time.
Yeah.
And you mentioned that software engineering cannot be treated similar to building a house. Can you explain a little bit why software engineering is different than the other types of engineering?
Yeah. Okay. So engineering is always about producing an outcome, a desired outcome within a set of constraints. I think in the sense that we can talk about software engineering, that's true as well. But let's talk about the other things first. You asked about the very common metaphor of software development is like building a house. That's a metaphor. I don't believe in that metaphor, but it's very common. And one of the problems is that the set of constraints is completely different, because when you build a house, you have some constraints that are imposed upon you basically by the real world. You have gravity, you have strength of materials, you have a lot of logistics you need to take care of. For example, you can't just start by building the roof and then later on say, well, yeah, I don't like the roof. Let's try to build another roof. And then later on, once you're done with the roof, you say, okay, let's now do the foundations. That's not going to work with the building, because the set of constraints is based in the real world. Whereas you also have a set of constraints in the case of software development, but the constraints are quite different. Often there's no implied order to things. So the example that I just gave, the way you can't start with the roof, there is an implied order to things. You have to sort of start from the bottom and go up if you're building a house. The constraints imply, or they enforce that order on the way you have to do things in a certain order. That's not so much the case when you do software development, because you can basically start wherever you'd like to start. If you want to start with the user interface, you can do that. If you want to start with a database, you can do that. So that's much more flexible. But then you have another set of constraints, and people are often not really aware of those. First constraint is the software needs to actually execute correctly on the computer. That's sort of like the bottom line. That's not the end goal. That's sort of like the bare minimum. But then you have all these other problems where you say, well, okay, so in order to be able to keep on developing on the software, developers will have to read the existing code in order to understand how to move next. So it's a little bit comparable to logistics in the sense that you can't build a house if you can't get materials on site. And if you excavate a foundation, you need to move all the dirt away from the building site. So there's some logistics in the real world. And I think it's a little bit comparable in the area of software engineering, in the sense that the logistics are more related to, how can you enable people to keep on working on adding more stuff to the software 6 months from now, a year from now, and 2 years from now. And the logistics that are involved in that is also the hygiene that is involved, because you have to make sure that the code is understandable to those people who come after you or just your future self. So that's also a set of constraints. So that's why I think that we can still talk about engineering, but it's just very different from physical structural engineering.